For half a century, the moon waited, silent, untouched. Humanity left, believing it would return. It never did. Until now. But Artemis is not another moon mission. It is something far more ambitious. This time, we are not going to visit. We are going to stay. On December 14, 1972, Gene Cernan stepped off the gray regolith of the Taurus Littrow Valley, pulled himself up the ladder of the lunar module, and looked back one last time. He was the 12th human being to walk on the moon. He would be the last for over 50 years. To understand why humanity abandoned the moon, we must look past the myth of the space race and confront the brutal realities of geopolitical physics. Apollo was born from fear. It was not built as an infrastructure project for human civilization. It was a Cold War sprint, a multi-billion-dollar demonstration of technological dominance. At its peak in 1966, NASA consumed over 4% of the entire United States federal budget. Over 400,000 engineers, scientists, and technicians worked tirelessly toward a singular metric of success: place a human footprint on another world before the Soviet Union. And once that flag was planted, the political impetus evaporated. The Saturn V rocket, the most powerful machine humanity had ever constructed, was cancelled. Production lines were disassembled. The massive blueprints were filed away in government archives. For 5 decades, the narrative prevailed that we stopped going to the moon because we lost our curiosity, or because there was simply nothing left to discover on a dead, dry rock. That narrative was entirely wrong. We didn't leave because the moon became less important. We left because we weren't ready to stay. If Apollo was a sprint, Artemis is a marathon. The fundamental architecture of Apollo was designed for maximum speed and minimal permanence. Astronauts traveled 3 days across the cosmic void, spent a maximum of 75 hours on the surface breathing bottled oxygen, collected rock samples, and fled back to the safety of Earth's atmosphere. They left behind flags, footprints, and trash. Artemis is engineered for the exact opposite. Where Apollo relied on a single nation and a single massive rocket, Artemis is built on a global coalition. An international alliance of dozens of nations bound by the Artemis Accords, partnering with commercial space giants like SpaceX, Blue Origin, and Axiom Space. Where Apollo searched for a flat, safe place near the lunar equator to land a tiny module, Artemis targets the treacherous, craggy terrain of the Lunar South Pole. Apollo was about reaching a destination. Artemis is about building a system. We are no longer building just landers. We are building a permanent orbital space station, the Gateway, positioned in a specialized halo orbit that allows continuous access to the entire lunar globe. We are building surface power grids driven by nuclear fission reactors. We are building autonomous processing plants designed to harvest local lunar resources and convert raw regolith into oxygen, water, and rocket fuel. The goal had changed. Humanity wasn't planning another visit. It was planning the future. To push human beings beyond low Earth orbit, you cannot compromise with the laws of physics. Escape velocity requires immense, violent force. To return to deep space, NASA constructed the Space Launch System, the SLS. Standing over 300 feet tall, generating 8.8 million pounds of thrust at liftoff, it exceeds the raw power of the legendary Saturn V by 15%. It is a machine built not for orbital efficiency, but for raw payload capacity. It is designed to push 37 metric tons, including 4 human beings inside the Orion capsule, directly into translunar injection. On November 16, 2022, the world watched as Artemis I ignited its solid rocket boosters. It was an uncrewed stress test designed to push the hardware to its absolute breaking point. For 26 days, the Orion spacecraft traveled 280,000 miles from Earth, further than any spacecraft built for humans had ever flown. It entered a distant retrograde orbit around the Moon, testing its optical navigation sensors, its deep space life support systems, and its radiation shielding. Then came the true test: re-entry. Orion slammed into Earth's atmosphere at 25,000 miles per hour, generating temperatures exceeding 5,000 degrees Fahrenheit, half as hot as the surface of the Sun. Its advanced carbon phenolic heat shield held. The parachutes deployed. Orion splashed down safely in the Pacific Ocean. The machine was proven. Now, humanity steps back on board. Four human beings are currently preparing to strap themselves into the apex of that immense rocket. Artemis II will not land on the surface. It is the ultimate dress rehearsal, a 10-day journey designed to carry human eyes further into deep space than any one in history. Their trajectory will take them on a sweeping, hybrid free return path around the Moon. As their spacecraft sweeps past the far side, something profound will happen. For the first time since 1972, human beings will float behind the bulk of the Moon. Earth will disappear. Every radio signal from home will be blocked by thousands of miles of solid rock. Every human being who has ever lived, every city, every war, every memory, will be hidden behind a wall of gray dust. They will experience a profound, total isolation, floating in a titanium pressure vessel 3 degrees above absolute zero, staring out into the unfiltered starfields of the deep galaxy. They will test the manual flight controls, verify the environmental life support systems, and observe the lunar surface with their own eyes to scout landing sites for the next crew. Artemis II will prove that our species can once again survive the deep space environment between worlds. And when they return, the door to the surface will open. When Apollo landed, NASA chose flat, smooth, equatorial plains. They were easy to land on, easy to illuminate, and safe. Artemis is heading somewhere entirely different: the Lunar South Pole. This region contains what planetary scientists call the most valuable real estate in the solar system. Because of the Moon's minimal axial tilt, just 1.5 degrees, the Sun skims parallel across the horizon at the poles. Mountain peaks like Malapert Mountain experience near-eternal sunlight, providing a continuous source of solar power. But just miles away, inside deep impact craters like Shackleton, the sunlight never hits. These crater floors are known as permanently shadowed regions, PSRs. For over 2 billion years, these crater bottoms have sat in total darkness. They are among the coldest places in the known universe, dropping to -380 degrees Fahrenheit. And inside that eternal cold lies gold. Not gold in metal, but something far more precious for a spacefaring species: water ice. Billions of metric tons of pure water ice preserved in the cosmic deep freeze since the formation of the solar system. Water is not just for drinking. Water is life support. Through a simple process called electrolysis, powered by solar arrays on crater rims, water is split into its constituent elements, hydrogen and oxygen. Oxygen to breathe. Hydrogen and oxygen combined to create liquid rocket propellant. The South Pole of the Moon is not a barren desert. It is a gas station in deep space. By harvesting ice on the Moon, we eliminate the need to haul heavy water out of Earth's deep gravity well. We transform the Moon from a distant destination into a refueling hub for the entire solar system. So how do we actually stay? It begins in orbit. The Lunar Gateway space station will serve as a command module, logistics hub, and refuge for visiting crews. Unlike the International Space Station, which orbits just 250 miles above Earth, Gateway will float in a near-rectilinear halo orbit, balancing the gravitational forces of the Earth and Moon. From Gateway, astronauts will transfer into specialized human landing systems. Massive vehicles like SpaceX's custom Starship HLS, a 50-meter-tall stainless steel spacecraft capable of transferring dozens of tons of cargo and crew directly to the surface. Once on the surface, the true engineering miracle begins. Surviving on the Moon requires confronting a brutal landscape. There is no atmosphere to shield against cosmic rays or solar flares. Micrometeorites hit the surface at 20 miles per second. And the dust, lunar regolith, is not smooth like beach sand. Because there is no wind or water erosion on the Moon, every particle of dust is a jagged, glass-like shard that destroys seals, tears spacesuits, and shreds mechanical bearings. To build a permanent habitat, we must use the land itself. Robotic 3D printers will harvest local regolith, mixing it with binding agents or heating it with microwaves to create solid concrete-like structures. We will bury our habitats under several feet of lunar soil, creating thermal insulation and thick radiation shielding. Surface nuclear reactors, compact fission systems delivering 40 kilowatts of continuous power, will run continuously through the 2-week-long lunar night when solar panels fall dark. This is the Artemis Base Camp, a permanent scientific station, a foothold on an alien world. Humanity will no longer be an visitor returning home after a weekend. We will have an address on the Moon. There is a fundamental truth about Artemis that is often overlooked. Artemis is not ultimately about the Moon. The Moon is a classroom. Mars is the exam. If a critical life support system breaks on the International Space Station, astronauts can board a Soyuz or Dragon capsule and return to Earth in 3 hours. If a system fails on the Moon, a crew can be home in 3 days. If a system fails on Mars, you are 3 years away from help. Radio signals take over 20 minutes to travel one way between Earth and Mars. There is no real-time mission control. There are no emergency supply drops. There is no turning back once you ignite the engines for the Trans-Mars injection burn. The Moon allows us to test closed-loop life support systems that recycle 99% of water and air for years without failure. It allows us to test deep space medical protocols, autonomous crew operations, and long-term psychological endurance under real cosmic radiation. It allows us to test how human bodies adapt to partial gravity, 1/6 on the Moon, 1/3 on Mars, before committing crews to a 6-month zero-gravity transit followed by years on an alien surface. If humanity is ever to become a multi-planetary species, if we are ever to build cities under the red skies of Mars or harvest the mineral riches of the asteroid belt, it all begins in the dust of the Lunar South Pole. The Moon is humanity's proving ground, the nursery where a planet-bound species learns how to walk among the stars. In 1969, a generation of human beings looked up at the night sky and realized that the boundaries of our cradle had been broken. The Apollo generation proved that we were capable of miraculous engineering when driven by a single purpose. Today, we are the Artemis generation. We are returning to a moon that is no longer a cold, distant trophy, but a dynamic world full of resources, scientific secrets, and infinite potential. Apollo changed history. Artemis will change the future. One mission proved humanity could leave Earth. The other may prove that we never have to live on only one world again. Because every civilization reaches a moment when it must decide whether to remain in its cradle or to step out into the ocean of space. Artemis is that moment.